For our project titled Reinforcement Learning for Mixed Integer Linear Programming Branch Heuristic Selection, we'll be going over some of the theoretical background and some of the methodology and results that we have for this project. So we'll get started with some of the background because it's a bit involved. We start off with the concept of linear programming, which you have a linear function subject to linear or affine constraints. And the number of these can be quite large, but they can describe quite a lot of systems that are quite complex and important to solve. Now here we're going to describe the main algorithm that our program targets, which is something called branch and bound. So let's say, for example, that our system, when unrestricted to integers, gives us a fractional solution, so say 0.42, but we want this to be an integer. So what we're going to consider are cases in which are less than equal to 0, greater equal to 1. Recall that the dimension can actually be quite high. So here, I mean, we have x3, but there could be thousands and thousands of this. And so looking into our notebook, we're going to solve a specific problem in mixed integer linear programming, but our scheme applies to general mixed integer linear programs. This one's called a set covering problem, which we describe in further detail in our write down. Now we form a Markov decision process that's based off this paper, Gass et al., in which we sort of provide some information and then the agent sort of makes some branching decisions based off of that. A set of heuristics to make, and that's the decisions. Decisions describe what type of heuristic you choose. Now, it is true that in the long run averages, some heuristics tend to beat out others, but it's not necessarily the case that one heuristic is always better than another one. So in that case, it can be good to find ways to decide on which heuristic is good. And so here we define a common interface for our agents. And we sort of define a common object and that we provide them and provide context for the next iteration. We describe here the implementation of our system as far as branching heuristics are concerned. And here we describe several different types of algorithms that we describe in class. So these are some from the textbook that we'll be describing here. And so going to the results, we see that, in fact, many are actually quite suited for this task and that they are able to decipher which choices are good. Some are a bit less stable, such as the bandit ones, can be a bit more unstable, which is not completely unexpected, given some of the uncertainty. Here we do see some fluctuations around the points for about all ones. This makes sense considering that some problems are more difficult than others. And so at each step here, or each point here, we are evaluating the same problem. And because some problems maybe can't even optimally be solved perfectly, we're not always going to get the same result. For context, the reason why these are not always rounded to integers is because we do have a rolling window, and that's just to not make just to make the graph readable. So we do have a window of 100, which sort of acts as a low pass filter in this context. At the end of this document, we do describe some challenges and possible future considerations. I would say some of the main challenges come from the scaling and sort of difficulty of running this problems and algorithms. It is the case that one small mistake when making a system can cause quite a long rerun, which is a case in many machine learning contexts. Now, for future work, I think one of the main considerations does have to do with scaling. And the reason for this is because once you're able to scale things and make more difficult problems, which are very simple, but time consuming given the libraries that we use, we'll start to see that the differences between individual algorithms are more pronounced. So we see here that the algorithms chosen for the class, more or less, or at least most of them, are able to do things quite well. However, as soon as we start scaling and making things more difficult, we expect to see some falter compared to others. And so difficult data instances could perhaps give us a better idea overall of some of the relative performance differences between algorithms.